All right, recording is rolling. It is Tuesday, October 4th. Here's our agenda today. All right, so we're going to start with the spring scale activity. You guys got some spring scales on your desk, right? Different color spring scales. Right. After we do this activity, take a few minutes, we're going to switch over and do Kahoot for the last conceptual questions. You guys remember this packet of 60 conceptual questions? We did the first, each of these are Newton's laws of motion. There are 20 on each of the laws of motion. So we're going to do Newton's third law of motion today, and that will complete this packet. Okay. So you guys get this out, ready to go. Okay. And then got your phones on and connected to the internet because we're going to do that. Okay. Then I just gave everybody a forces quiz for open notes take-home quiz. Did anybody not get this take-home quiz? So everybody, or yeah, you got one, right? Okay. All right. So everybody's got this open notes take-home quiz. All right. So I definitely need this one by Friday for sure. That and also your packet of conceptual questions. Right. This is your homework that's due Friday, and then you guys have an open notes take-home quiz. Both of these things are due by Friday, right? You guys got that? Right. If you want to turn these in early, like tomorrow, that's probably a really good idea because this Friday is a hard deadline. You guys know that this Friday is the last of the first quarter, right? We're about to close out the first quarter, right? So definitely need all this stuff sometime this week. Turn it earlier the better. Okay. All right, so let's hit this spring constant activity with the spring scale. So guys, find a spring scale. Do you guys find a spring scale that's not brown? There might be some brown ones, but ignore that. Find either a green scale, a blue scale, a white scale, a red scale, or a gold scale. You guys got one of those? Okay, so I'll use the brown one as a model. And when we started this section, dynamics, I gave you guys actually I've got it right here. You guys remember these 10 mini labs, right? Using the spring scales. But you had to know how the spring scale works. So I introduced this whole topic with something called Hooke's law. All right, we're going to go back to that to wrap up the section. Hooke's law. You guys remember what Hooke's law is? Right? It gets at the spring right here. Right. So each scale, well, whatever scale type it is, whatever color it is, right, has an associated spring with some stiffness. Right. And that means that if I put some force on it, it's going to stretch some amount. Okay. And that relationship, well, that's Hooke's law. So suppose you have a spring. Here's a spring right here. And maybe it has no force on it. It's just unstretched, uncompressed. It's just hanging out there, right? Now I'm going to put a stretching force. I'm going to stretch it some amount. Okay, like this. Okay, so here's a force this way, and an equal and opposite force pulling this way. Right? Stretching it out. And oh, look how much it stretched out. It stretched out by this much right here. And the amount that it stretched, I'm going to call x. Right? Now, guys, if I put some force on it, and it stretches by that amount x, that only is going to happen exactly if the spring itself had a stiffness of some amount k. Guys from that? Oh, spring constant or spring stiffness. Right? And what's the formula that ties these three variables together? F equals what? Kx. Exactly. Right. Some textbooks throw a negative sign in there. It depends on what force you're looking at. Okay. But got F equals Kx. Okay. All right. So hey, if the question is what here, this question we're getting at, what is the spring constant in this brown scale? We'll start with just brown one. So I'll use this as a model. Okay. So when I'm solving for this K, right? Okay. Hey, if I knew what force I put on it, which it has a metric on it, you just read straight off the tube, right? I know how much I stretch it at. Yeah, I've got a ruler here. I could just see like how hard it stretched. Okay. Can I pop those numbers in and solve for K? Right. Actually, let me do this. I'm going to do the algebra first, right? Which I don't do very often with you guys, but let's do that first. Let's solve it in terms of variables. That's another way to say that. Right? Can you solve for K in terms of F and X? And it's one algebra step, which is what do you do both sides? Divide by X. Exactly. Right. So I can say K is just F divided by X. Right? That's just a rearrangement of Hooke's law, isn't it? Right. All right. Now with the Brown scale, let's see. If I put 10 newtons of force on it, that pretty well maxes out the scale. 10 newtons of force. Okay. So we're gonna do that. I'm gonna put in 10 newtons right there. 10 newtons. And how far did I have to stretch it for that to happen? Oh, you guys know we're looking at the side that says newtons, not the side that says grams, right? Right. So we're focused on the side that says newtons because newtons measures force. Right. And how much did I stretch that? What? Got a ruler. So that looks like 5.2 centimeters. So that's 5.2 centimeters of stretching that you get from applying 10 newtons. Okay. So let's divide that out. What is 10 newtons acting on 5.2 centimeters? That is 1.92 newtons per centimeter. You guys remember in physics, all your numbers have units attached to them, right? Well, with a couple of exceptions, but okay, there you go. 1.92 newtons per centimeter. Okay. Now that's all fine and good, but a more standard way of expressing spring constant is in terms of like newtons per meter. Hey, I wonder, let's do some dimensional analysis. How many newtons per meter is that? So 1.92 newtons per centimeter. You guys remember doing this trick with like the railroad tracks? A little dimensional analysis going on here. Guys, how many centimeters are in 1 meter? 100. 100, right? Same thing as 100 cents in a dollar. 100 centimeters every 1 meter. Is that true? Could you call that 192 newtons per meter? Is that true? So I could say that the spring constant for the Brown spring scale is 192 newtons per meter. Another way to contextualize that is suppose I had a really long spring, really long spring, okay? And it was equally stiff as this one is right here. So if I was like blindfolded and I pulled them with some force or some stretched them out, I couldn't tell the difference between this one and the really long one, right? So equally stiff. And I put 192 newtons of force on the really long spring. How much is it going to stretch? How many say 1 meter? Yeah, 1 meter. So if I had a really long spring that was equally stiff, and I should pull 192 newtons, it would stretch 1 meter. That's what 192 newtons per meter is, right? Of course, this one's really short, but it's the same ratio, right? You guys got that? Okay. Now, I'm wondering from you guys. Right, so you guys got some spring scales at your desk? Okay. Well, let's get a few of these. All right, so here's some opportunities. I know there's a blue scale out there. I know there's a green scale out there. I know there's a gold scale out there. I know there's a red scale out there. And I know that there's a white scale. Okay. I forget exactly how they rank, but I do know this. I do know that compared to the brown scale, the blue and the green are not as stiff, and the gold, red, and white are more stiff. I remember that at least. Right? So here, I know that K Brown is 192 newtons per meter. Okay. So let's get at least a couple of these before we do the Kahoot. Okay. Let's get a couple more spring scales. There's 5 options. Okay. Can you guys figure these out? Okay. Please figure out one of these. We'll do 2 of these, and then we'll flip over to the Kahoot. Get the rest of those answers. Okay. All you have to do is exactly what I did. You can see one of the force readings. You can break out your ruler, measure how many centimeters is that. You can get newtons per centimeter, right? And then just multiply by 100 to get newton per meter. Right here, let me show my math work on this. Okay, here's what I did for the Brown scale. Can you do that for one of the other scales? All right, who's figured out one of the scales? Anybody figure out one of them? Oh, yeah, got one of them?
For the green one.
50 for the green? I can believe that. That sounds about right. You're saying about 50 newtons per meter. Yeah, I haven't checked it myself, but I do know it's less than the brown, so that looks believable, right? Yeah, so let's go with that. Yeah, what you got, Cole?
On blue one, 48.
48?
I think so, yeah, 48.
Huh. Okay. You know what? They shouldn't be too close to each other like that. Let me see myself. Let me grab a green one and a blue one. Okay. This is okay. All right, so start with the green one. All right, so the green one goes up to only 5 newtons. And what is that distance right there? That distance is it's also 5.2 centimeters. So if you do 5 newtons on 5.2 centimeters, and then multiply by 100 to convert to newtons per meter. I'm getting closer to like 96 for this one. It's 96 newton per meter. Okay, and then the blue one goes up to 2.5 newtons. Right, so this is a real loose spring right there. Hardly any stiffness at all. Right, because 2.5 newtons will also take it to 5.2 centimeters. So 2.5 newtons on 5.2 centimeters, then multiply by 100 to convert to newtons per meter. Yeah, I'm getting what Cole got there is 48 newton per meter for the blue one. All right, so there you go. There's a few of them. And if you picked one of these guys, you get a number that was greater than 192 newton per meter. All right. All right, so you guys good there? All right, so let's get up here. Okay, so you guys got your conceptual questions out. Okay, so remember we've done the first law and the second law already. Right, those go back up for the hurricane. All right, we're about to knock out the third law of motion right here. So flip my screen over. All right. Oh, Kahoot's up there, ready to go. All right, you guys go ahead and hop on. All right, and here we go. Newton's third law of motion. Whenever an object exerts a force on another object, the second object exerts a force same magnitude, opposite direction on the first object. Yeah, that is a statement of Newton's third law of motion, isn't it? That's exactly what Newton's third law of motion says. That is always true. Always true. Evan in the lead. High school student hits a nail with a hammer. During the collision, there is a force. What? Yeah, on both the nail and the hammer. But which force is bigger? The force from the hammer on the nail, or the force from the nail on the hammer?
The force on the nail from the hammer.
For every force, there's an equal and opposite. All right, it's the same force, right? Same force. All right. All right, Evan's still in the lead. Archer shoots an arrow. Consider the action force to be the bowstring against the arrow. What's the reaction force? Bowstring pushes on arrow. Reaction. Yeah, the arrow pushes us back against the bowstring. So equal and opposite. Oh, David on fire, moving up. Evan's still in the lead. Player catches a ball. Consider the action to be the ball against the player's glove. What is the reaction force? Ball hits glove. All right. You guys are getting this. Yeah, the glove back on the ball. Ball hits glove hits ball. Which force is bigger, though? The ball hitting the glove or the glove pushed back against the ball? Are they
They're equal. Same.
Equal, same, aha, same force. All right. Evan on fire. We got David, Cole, Zach, and Capri. Round out top 5. Player hits a ball with a bat. The action force is the bat against the ball. What's the reaction force? Yeah, the ball hits the bat. The bat hits the ball hits the bat. But which force is bigger? Ball hitting the bat or the bat hitting the ball? Ah, same force. Ah, good guys. Zach moving up. David, Evan still in the lead. As the ball falls, the action force is Earth's mass pulling on the ball. What's the reaction force? So the Earth is pulling on the ball. All right, here you go. What you got? Yeah, so the ball pulls up on the Earth, right? So the Earth pulls the ball down. The ball pulls the entire Earth up. Huh. Okay, now for that one, which force is bigger? The Earth pulling the ball down or the ball pulling up on the Earth? It is the same. It's the exact same force. Right? Hang on a minute. How could it be the same? Because the ball's like accelerating, right? But the Earth is like not really moving. Right? Why is that? Because the Earth has so much what? So much mass, right? So much mass, so much inertia, right? So it's the same force, different masses, different accelerations. You have to kick back to Newton's second law of motion for that one, right? All right, same force. All right. Evan on fire in the lead. Got David, Zach, Capri, Liam. Top 5. Unfortunate bug splatters against the windshield of a moving car. Compared to the force of the car on the bug, the force of the bug on the car is the same force, same leaders, same scenario. Compared to the change in motion of the car, the change in motion of the bug is what? You know, the forces are the same, masses are different. Ooh, got one winner. Yeah. Okay, so remember, even though the force is the same, if you kick back to Newton's second law of motion, which we did a while back, right, same force acting on a smaller mass results in a larger acceleration, right? See, like the change in motion bug's just like floating around like la-di-da-di-da, and then all of a sudden, bam, gets hit by a windshield. Huge change in motion of the bug during that tiny fraction of a second. But what about from the car's point of view? The car's just going along like, just barreling, then it smacks into a bug, like, right? Does the car change its motion very much at all? Hardly at all. It's like negligible, right? Maybe a tiny bit. Right. But unless the car's like plowing through a billion bugs, just like, right? Car's not really gonna notice, right? Even though it's the same force, but a huge mass, very small acceleration for the car. Right? Car hardly slows down at all. Right. And David's taking top spot with that one. I got Evan, Zach, Capri, and Liam. Top 5. Horse pulls a wagon at rest. The wagon pulls back equally on the horse. Can the wagon be set into motion? Yes, why? All right. Yeah, the one they're looking for is there would end up being a net force acting on the wagon. Part of the explanation for this too is that there's more than just the horse and the wagon going on here. There's also the ground that the horse can push against. So there's a friction force. So there's like a third object that they're pushed against, right? See, like if they were in deep space and it was just a horse and a wagon in deep space, then no one could really move anywhere, right? But they're pushed against the earth. And the wagon, there's a net force on the wagon. Yeah, the textbook material this comes from, there's like a whole page, like a whole like cartoon where they go through and like explain this one. So that one takes some thinking, but yeah, end of the day, that's the best answer there. All right, and Cole's hopping in the top 5. David still got the lead. Large truck, small car traveling same speed have a head-on collision. the vehicle to undergo the greater change in velocity will be the what? Yeah, it would be the smaller mass, in this case, the smaller car, right? Even though the force interaction is the same, they both get the exact same crunch force due to the crash, due to the collision, right? But that force acts on different masses, therefore different acceleration. Hey, which vehicle would you personally be safer in during the collision? Would you rather be in the large truck or the small car? Large truck, right? Because large truck's not going to change its motion as much, so you'd be safer as a passenger. Got Capri moving up. Liam hopping in. David still in the lead. According to Newton's third law, if you push gently on something, it will push. How? Yeah, gently on you, right? Equal and opposite. Right? So same magnitude of force, opposite direction. Action reaction. All right, Capri moving up. David still in first. Earth pulls on the moon pulls on the Earth. Yeah, those are both true statements. So Earth and Moon are pulling on each other. That's an action-reaction pair. Which force is greater, though? Earth pulling on the Moon or the Moon pulling on Earth? They're equal. Equal and opposite, right? You know what? This is actually a really good segue question to the next topic that we're going to start tomorrow. Next topic we're starting tomorrow is actually a few topics put together. We're going to do like centripetal force for like a circular motion, anything moving in a circle. We're starting to get to curve paths starting tomorrow, right? We're also going to talk about universal gravitation, and we're going to take those two ideas and put them together. If you have universal gravitation, and you could get like a centripetal causing a centripetal force, okay, you can create an orbit. So we'll get into orbits. All right, so I'm gonna start tomorrow. All right, got Capri, Zach, Liam, Evan, David on fire. Nellie Newton holds an apple in her hand. If the action is Earth pulling on the apple, what's the reaction? See, Earth pulls on the apple. What's the reaction? Oh yeah, I forgot. This is a tricky question. Wouldn't the reaction be the apple pulls up on the Earth, right? So the Earth pulls down the apple pulls up on the Earth. All right, and that just wasn't an option. Oops. All right, you guys get that? All right. Bronco, skydiver, falls toward Earth. The attraction of Earth on Bronco pulls him down. What's the reaction force? See, the Earth is pulling on Bronco. Yeah, Bronco pulls up on the Earth. Right, so Earth and Bronco pulling on each other. Ooh, Evan back in first. Got David, Liam, Capri, Zach rounding out top 5. Force exerted on tires of a car to accelerate the car along a road. The force is exerted by what? What's actually driving the car forward? Oh, yeah. How about the road, right? Isn't the road like pushing on the tires, like with like a friction force, right? You guys ever tried to drive without friction? Yeah, I know we don't get very much like iced over roads here in Florida, but here, how about play a short clip for you guys? Wow. All right, they're in a magic textbook with no friction. You have a frictionless baseball field.
The game, DA.
We can come back to this later
On the
too.
mound is Wanda, one of the most outstanding pitchers in the class.
And master of the
Wow. So no friction, everybody's just sliding around, right?
Wanda used really got that ball going and pushed her way back towards second.
It's a
All right, so we'll come back to that one someday. but yeah, you gotta have friction push gets to get going, get your car going, right? Rocket is able to accelerate in the vacuum of space when it fires its engines. The force that propels the rocket is. Yeah, the force of the exhaust gas on the rocket. So the rocket is pushing the exhaust gases out the back, and the exhaust gases are pushing the rocket forward with an equal and opposite force. Rocketry. All right, wish you guys got that. Evan, hold on to the lead. A few questions left. Karate chop delivers 1900 newtons to a board that breaks. The force that acts on the hand during this feat. Got 1900 newtons on the board. What about on the hand? 1900 newtons. All right, same force, same force. This person weighs 450 newtons, sits on the floor. She exerts a force on the floor of 450 newtons. Oh yeah. Same scenario. The floor exerts a force on her of yeah, same force. Equal and opposite. You got Evan on fire, David, Liam, Caprice, Zach. 1 and 2. Last question. 2 people pull on a rope in a tug of war. Each person pulls with 600 newtons of force. What is the tension in the rope? $600 newtons. All right. All right. 3 of you guys got that. All right. If everybody's pulling 600 newtons, the tension in the rope is 600 newtons. To the winner's podium. With the bronze, Liam. With the silver, David. And the gold, Evan. Oh yeah, Confetti Dance. Runners up, Capri and Cole. All right, nice job, guys. Confetti Dance. All right, next thing.
So no matter what the force is, always gonna be equal to like
Yeah. So whenever you have 2 different objects like pushing or pulling on each other, yeah, it's always equal and opposite forces. Okay, so you have to have 2 objects, force interaction. Yeah, always equal and opposite. All right, there you go. See if you isolate one object, well, not necessarily unless it's like equilibrium or something, but yeah, 2 forces or 2 objects, equal and opposite forces. All right, let's do let's do a quick review of let's do an Atwood. That's what we're gonna do. We're gonna do an Atwood, and then we'll switch over and we'll finish the class with some videos. That's how we're gonna do this. Okay. So let's say I got a couple of masses slung over a massless frictionless pulley. I'll call, let's say the little mass is like 5 kilograms, and the big mass is like let's go 19 kilograms. Right, just pick some crazy numbers. Right. I might want to know what is the downward acceleration of mass B, the large mass. Okay. So this whole thing is going to accelerate clockwise. Zoop, zoop. Okay. So what's the downward acceleration of this guy? Okay. I could have a follow-up question. Here? How about this? What is the tension in the string? Okay. Now, just in case you guys ever take physics in college, there are different ways to approach this problem. And one way of approaching it, you actually answer these questions in reverse order. But let me just the same way as I've been doing it in class. Right? And so we're going to answer this question first and then this question. Right. Let's look at some forces. Let's do free body diagram, FBD. So, guys, how much does 19 kilograms weigh in newtons? How many newtons of force is that? Yeah, 190, right? Because 19 kilograms times 10 meters per second squared, 190 newtons, right? How much does 5 kilograms weigh? 50 newtons. All right, got 50 newtons. Okay. Actually, I could just stop right there and answer the first question. Couldn't I do that? Right. So we could do that. I see there's a net force on some total mass causing an acceleration. Acceleration is net force acting on some total mass, right? And what is the net force in this tug of war? You guys see 140 Newton net force, right? So it's 190 minus 50. There's 140 Newtons right there. Acting on how much inertia? You guys see 24 kilograms, right? It's got 19 kilograms plus 5 kilograms, right? Is that true? Okay. Let's do 140 Newtons acting on 24 kilograms. I'm getting 5.83 meters per second squared. Oh, I meant to ask you guys before I started plugging and chugging. Do you think it would be closer to pure free fall or closer to 0 meters per second squared? And actually, it's about halfway in between, isn't it? Right? Because the two boundary conditions, like the two extremes, are you could either have these the same mass and the same weight, in which case it'd be 0 acceleration. You just kind of hang out there. Or the other extreme is you could put all the mass, all the weight on one side and be like pure free fall. So there's an empty string hanging out the other side, and right? That'd be 10 meters per second squared. Right? And yeah, okay, this is somewhere in the middle. Right? Oh, that's the first question. Bing, answer that guy. Right? There could be this follow-up question. What's the tension in the string? Now to do that, and then you go back and add some forces. Okay, so I have the two external forces. Those are the ones that drive the system. But there is an internal force that's holding everything together. And I know it's greater than the small weight, but it's also smaller than the big weight. It's like a Goldilocks force, this tension force. So it's the same magnitude. But there's a net force driving the small block up and a net force driving the large block down. Right, guys, that right. Let's go figure out what is that tension. So to do that, now I have to just focus on one of those blocks. Right. Well, let's focus on a little guy. Why not? Just eeny, meeny, miny, moe, coin flip. Right. Let's do this guy right here. This guy right here. I could set up F net equals mass times acceleration just for that single block, right? And what is the net force? Isn't it the tension up minus the weight down? You guys see that? So this net force is the tension force up minus 50 newtons down. Isn't that true? Okay. That's equal to a 5 kilogram block accelerating at well, we know how much it's accelerating upward. That's what we figured out before, right? 5.83 meters per second squared. Right there. Okay, so I can multiply this together, and then there's just one algebra step. Let's just take 50 newtons and add 50 newtons over. So 5 times 5.83. This is all 29. Right. Add the 50 over, and the tension force must be 79 newtons. There you go. 79 and change. So I'll call it 79. Okay, you guys get that? Okay. So 29 plus that 50 is 79. Okay. You know what? Let's check our answer. Let me switch over to the other block. Right? Because isn't it the same tension force? Okay. Got one string, one tension. 79 newtons. Guys, what's 190 minus 79? I'm getting 111. That's the net force on this block, right? And net force of 111 newtons acting on 19 kilograms was 111 newtons acting on 19 kilograms. Now this number's rounded a little bit, so it won't be exact, but as a general idea, there's only one number that can pop up on my screen. What does the answer have to be? The downward acceleration of this block has to be what? this right here, because we already solved it from a systems point of view. Now I'm just getting micro, more granular, but it has to be about 5.83. Yeah, plus or minus a little bit. Let's see. Yeah. So same 5.84 because it's 111 is rounded a little bit, but that's it. Ding. It's the tension string is 79 newtons. Okay. All right, you guys get there? All right, any questions about anything? All right, so I'm gonna flip the screen back over and we're gonna finish this unit with some videos we're gonna go out on. All right, it's fine. Ooh, here's a pretty good one.
But this is going to be really tough to see. So how are we going to actually determine what the right answer is?
If I were to drop it now, it would happen so fast you wouldn't really see clearly what's happening. So I've brought along my slow motion camera and you'll see it at 300 frames per second. And it's quite spectacular.
Well, that's ultra slow-mo. So that's exactly what we need to sort out this problem.
We'll give a countdown because it happens really fast.
All right.
3, 2, 1, drop.
Wow, did you see that?
I didn't really see which happened first. No, I need to slow that down.
Well, let's go to a slow motion replay and see what actually happened.
Okay, thank you.
So from the slow motion camera, we can clearly see that the bottom end stayed completely stationary even after you let go of the top. It waited until the whole slinky had collapsed down to the bottom before it itself moved downwards. How do we explain that?
Well, there are a number of explanations, but the simplest explanation is that the bottom end is sitting there minding its own business with gravity pulling it down and tension pulling it up, equal and opposite forces, no motion at the bottom end until the bottom end gets the information that the tension has changed. And it takes time for that information to propagate down through the slinky to reach the bottom end. So it's propagating down as a compressional wave.
And we saw that compression wave travel down, and it has to reach the bottom before the bottom even knows that you've let go at the top.
Correct.
And that's when it knows to start falling.
Correct.
That's a really remarkable finding. I mean, does this apply to any other objects, or is it just slinkies?
No, it applies to the real world, particularly in sports, which is the field I'm interested in. For example, when a player hits a ball, there's a huge force at the business end, but that force is not felt at the handle end until the ball is well on its way. So a wave has to propagate from the business end down to the handle end, and then it propagates back again. And what you actually feel down this end is considerably less than what the ball felt.
So, wow, if you're playing tennis or something, you only feel that you've hit the ball after you've actually hit the ball.
A force is an interaction between, in this case, my hand on the wall, if this is a wall, and what's the reaction? That'd be the action force, hand on wall. What's the reaction, gang? Wall on hand. You can't push on something without being pushed back. Could you hold this rock? We're gonna have a tug of war here. Okay, Helen's gonna pull the rope that way, and I'm gonna pull it this way. Now, who's bigger, me or Helen? Yeah. Okay. Okay. Now we pull. Okay. Now who's pulling harder? Am I pulling her harder or is she pulling me harder? How are we pulling, gang? Check the neighbor on that one. What do you suppose? Is she pulling me harder or am I pulling her harder? Huh? Who's pulling harder? Is that so? You used to say, I'm pulling harder because you see the rope moving this way. That's what you used to say. Remember the old days? When you didn't have that spark called what? Begin with an F. Physics, all right? And now you're getting that spark, right? And now you're starting to see the world a little differently. Let's try this with a couple of scales. I'm gonna attach this right on here. Okay, now you pull that side and we can measure the force, gang, yeah? And I'll pull over here. Now you look to see who pulls harder, me on Helen or Helen on me. And here we go. How do the readings look, gang? Huh? Which one's harder? How about there? How about there? And what are they, gang? SS. Same. I can't pull on you any harder than you pull on me, okay? and you fire a rifle. Here's the bullet. Bullet races out. And the bullet has a force acting. But that gun kicks back. How much force? Really the same? The same. The same force acting back. Now, the acceleration of the bullet, a lot or a little. Answer begins with an L. A lot. Because here's the mass of the bullet. Here's the mass of the rifle. So here's the acceleration of the bullet. Boom! But here's the acceleration of the rifle. So the rifle only goes back to here. And the same time the bullet goes from here to here. That bullet is accelerating like bonkers, right? Inside the barrel. Now, when it gets outside, is it still accelerating? No. Now it coasts. We talked about this before. It's accelerating down. Why it drops. It follows the curved path. But while it's inside, the forces are the same, but the masses are different. That means that the effects are going to be different.